Hey everyone, Professor Baldwin here, and today we're going to learn how to solve equations and inequalities with absolute value. Remember that absolute value is distance. So it's how far you travel from a point, and positive or negative tells you the direction. So absolute value eliminates that plus or minus, so we're really looking at distance traveled. So look at example 1. We're trying to find the absolute value of x equal to negative 10.7. So this is saying your distance is negative 10.7 steps. Is it possible for you to walk a distance of negative 10.7 steps? No, it's not. So there's no solution. Right? If we start at this point here, there's no way to travel anything less than 0. If we travel 0 units, we stay exactly where we are. If we travel 1 unit, we could go 1 unit to the right, or we could go 1 unit to the left. Look at example 2. We're looking to find a distance that's equal to 17. Well, this is possible. We can go 17 units to the right or 17 units to the left. 17 units to the right would mean taking the value inside the absolute value and solving when it's equal to 17. 17 units to the right. And to go left, we solve when it's equal to negative 17. So here the negative denotes that we're going to the left. Let's solve the first. Add 5 to both sides. We have 1/2 x equals negative 12. We multiply both sides by 2 to get rid of the 1/2. And we have a solution that x equals negative 24. The second possibility, we add 5 to both sides. We have 1/2 x equals 22. Multiply both sides by 2, and x is equal to 44. So when x is negative 24 or x equals 44, the absolute value here is equal to 17. Now look at example 3. We have an absolute value minus 4 equals negative 1. Well, when you're solving an absolute value, you need to isolate the absolute value first, and then you can evaluate it. So let's add 4 to both sides, and we see that we have 3x plus 1, absolute value, equals 3. This we can solve because it's looking at a distance of 3 units. Remember, if we go left, we're solving that absolute value equal to negative 3, and to the right, 3x plus 1 equals positive 3. For the first one, subtract 1 from both sides. We have 3x equals negative 4. Divide by 3, and our first solution is x equals negative 4/3. Second, let's subtract 1 from both sides, and we have 3x equals 2. Divide both sides by 3, and our second solution is x equals 2/3. Now, how about example 4? Remember, we need to isolate that absolute value. Let's subtract 12 from both sides to start. That'll leave a negative absolute value on the left equals negative 7. We're going to multiply both sides by negative 1, so that'll give us a positive absolute value of x plus 6 equals 7. Now we can solve this. We're solving x plus 6 equals negative 7, and x plus 6 equals positive 7. For the first, we subtract 6 from both sides and get a solution that x equals negative 13. For the second, subtract 6 from both sides and we get x equals 1. Pretty straightforward when you're solving absolute value equations. Now let's go on to page 2 and look at solving absolute value inequalities. The very first example, we have an absolute value that's less than. It can be less than, it can be less than or equal to. When you have the equal, it just changes your interval notation from parentheses to brackets. Now, let's look at graphically what a less than looks like. It's saying if we start at some point here and we're traveling less than a units. Well, to the right would be a positive a, and to the left would be negative a units, right? Now, if we travel less than a, that means we'll travel up to that point, but not past it. So less than for an absolute value inequality is going to give you this 3-part inequality notation. Now, look at what we get when we have a greater than. So again, we're starting at some point, and we can go a to the right and negative a to the left. Here it's saying we have to travel more than a units. So more than a units would be anything past those a's. So it's the outside pieces of our interval. So that gives us an or inequality, where we're solving both ends of our number line. Let's look at some examples. The first example, we have a less than. So that means our x needs to fall between 2 and negative 2. And if we put that in interval notation, I love these 3-part ones because it tells you that x is between negative 2 and 2. It goes right to interval notation. Now, example 2, we have a greater than or equal to. So that's going to be the second example. So it's going to be the outer parts of our number line. So we know that x has to be greater than or equal to 4.5, and x has to be less than or equal to negative 4.5. So it has to be smaller or bigger. And this might be easier to see if you put on a number line. So if you have 4.5 and you have negative 4.5, this x less than or equal to negative 4.5 is going to be shaded to the left, and the greater than or equal to 4.5 is going to be shaded to the right. So it's going to give us 2 intervals. The first is negative infinity through negative 4.5, and because of the equal sign underneath, we have a bracket. And then we have our second interval, again with a bracket, goes from 4.5 to infinity. Remember, infinity and negative infinity always have parentheses because we can't get there. And to combine those 2 intervals, we use the union symbol. Okay, 2 more examples here. We have the absolute value of x plus 8 is less than 9. That means our x plus 8 has to be within the range of negative 9 to positive 9. So we solve this 3-part inequality, subtracting 8 from all 3 parts. So we have negative 17 less than x less than 1. And again, these tell us pretty simply that x is between negative 17 and 1. And if we need to, we could put it on a number line. Our key numbers are 1 and negative 17. We have parentheses at each of them, and we shade in between. Now, example 4, we have a greater than. So we know that the value inside that absolute value has to be less than -5, or it needs to be greater than 5. We need to multiply by 3 first. So we have 2x plus 1 is less than -15. We're going to subtract 1. We have 2x is less than -16. Oh, give me a 6. Divide by 2 and we get x is less than -8. Solving the second one, again we multiply by 3 and we have 2x plus 1 is greater than 15. Subtract 1 and we have 2x is greater than 14. Dividing by 2, we have x is greater than 7. Let's look at 2 more examples. This first example is looking for the absolute value of 2x minus 4 is less than -5. Think what this means first. So it's saying we're starting at some point, and our distance, so this left-hand side is just distance. Just read it as distance. Your distance traveled is less than -5. So you're at home, and you're going to travel less than -5 units. Can you travel less than -5? Never. You can never go less than. You have to go at least 0. So there is no solution here. That's because you cannot go less than a negative. Now look at example 6. Here, our distance is greater than or equal to a negative. So think about this again on a number line. You're here at home, and you're going to travel more than -4 units. Well, what numbers are bigger than -4? Everything is bigger than -4. So if you go nowhere, you stay home, you've already satisfied that because 0, staying home, is bigger than -4. So this is all real numbers, or the interval -infinity through infinity. Don't fall for this trick. Number 6 is a tricky problem. We're very used to you can't have an absolute value equal to a negative or less than a negative, but you can have an absolute value that is greater than a negative, which is what we have in example 6. I hope this was helpful. If you still have questions or you have a specific problem you want help with, leave it in the comments or send it to me via email and I'll help you out.